Hello everyone. In the previous videos, we had introduced you to probability density function and cumulative distribution functions of a random variable. So now, in order to improve our understanding, let's see an example of a random variable and how to calculate its cumulative distribution function and probability density function. So let's jump right into the example. Now, let's say we have a hypothetical unfair dice with only three faces 1, 2, and 3. So, we know that usually dice has a 6 faces, but let's say this dice has only 3 faces and it can only show either of these three values 1, 2, or 3. So, we first of all form a sample space omega, which is this 1, 2, and 3, which will give you the possible outcomes of a dice roll. Okay, so we have an experiment in which we roll this hypothetical dice, and 1, 2, or 3 could be the possible outcomes. So we first of all define a sample space omega, which has three outcomes. So let's say it has three elements inside it 1, 2, and 3. This will give you all the possible outcomes which can be present in the dice roll. Now, let's define a sigma algebra F. Here in this case, we are defining F as the power set of omega, which can also be represented in this manner. A power set is basically the set which contains all the possible subsets of omega. So you can say that F contains like phi and omega, the null set and omega itself, and all the other subsets which are present. Now, in order to represent F, we can write it in this manner. So let's say this set 1, this is present in F. Let's say we have a set of 2 and 3, which is represented by this. This is also present in F. So this, in this example, like and in generally, the sigma algebra F will contain all the events, and that's why F is also known as the event space in many of the notations. So what's an event space? An event space is the set of all the possible sets which can be deemed as event of an outcome. So for example, let's say we roll a dice and the outcome can be, let's say the outcome is 2. So this is an event in this case. Now let's say I define an event such that I roll this unfair dice and the outcome can be either 1 or 2. Then in that case, this is the event. And we would find the probability of the occurrence of this event. So in this case, we have defined our sigma algebra F as the power set of omega, and it is also known as the event space. So now, and we have seen that as sigma algebra F is power set of omega, so this will satisfy all the properties of a sigma algebra. To learn more about sigma algebra, you can watch our previous videos. Okay, now we have defined the sample space omega and the sigma algebra F, which can also be called as the event space. Now let's see if by defining a probability measure we can form a valid probability space. So let's say this is the probability measure as given here, and we know that a probability measure is basically a measurable is a type of a measure. So we know that the properties of measure mu would apply to it. Now let's see if it satisfies the condition of being a probability measure. So as we know, mu of 0 should be 0, mu of phi should be 0, as the measure of a null set is always 0, and it satisfies this property as probability of measure of phi is 0 as it is defined here. Now the extra condition of a probability measure where p of omega should be 1 is also satisfied here. And if we map the events present inside the sample space omega to a real number line, we can see that it maps the probability measure maps between 0 to 1. So that means, let's say I take this event 1 and I apply the probability measure to it. So P of set 1, this would give us the value 0.2. So this will map to this value 0.2. Similarly, if I apply the probability measure to this event, it would map to, in this case we can see it can map to 0.3. And we can also later on verify that it also satisfies the probability of being a measure, as P of, let's say, disjoint sets, the union of disjoint sets will also be the summation of individual probabilities of those disjoint sets occurring. We can also verify it, where AI, AJs and rest of them are disjoint in nature. Hence we can say that since P satisfies all the properties of being a probability measure, hence in this case this omega, F and P form a valid probability space. Now let's see how we can define a random variable x in this example. So in this example we have defined a random variable x such that it will take the value of -1 if the outcome is 1, it will take the value of 0 if the outcome is 2, and if it will take the outcome as it will take the value of 1 when the outcome is 3. Now we know what a random variable is, right? A random variable is a measurable function which will map to a real number line from the sample space omega. So let's say this is the real number line, goes from -infinity to infinity, and we map our random variable like this. So x of 1 would map to -1, x of 2 will map to 0, and x of 3 will map to 1. And we can also prove that this is a valid random variable, as you can take any Borel set present in this real number line. It will always have a pre-image present in the sample space omega, and that pre-image would always be a part of the sigma algebra F. So we can say that if we take any Borel set, let's say B, present in the real number line, and then if you take the pre-image of it, which is x inverse of B, this will always belong to our event space F. Hence x is a real valued random variable. Now that we have proved that x is a valid random variable and this is a valid probability space, let's calculate the cumulative distribution function of x and the probability density function for the random variable x. So let's calculate this. So we know that we had defined the cumulative distribution function as the probability measure of the pre-image of x when the Borel set is in this format. It goes from -infinity to small x. So let's see from our visual representation how we can compute the cumulative distribution function of x. So this is omega, and this is the real number line, -1, 0 and 1. So let's say I take my value of small x being less than -1. So small x right now takes up this value. So any Borel set where, let's say, this is small x and it goes from -infinity to small x, in this case if I take any Borel set B, let's say this Borel set is B, and I take the pre-image of it in my sample space, I know that in such a case my x inverse of B would point to the null set phi. And I also know if I take the probability measure of x inverse b in such case, it would be the probability measure of phi, which is 0. Hence, for all the values of small x being less than 1, the f of x of small x would be 0. Okay, so let's start writing it in a better way. So when x is less than minus 1, this value is 0. Now let's take small x to be between minus 1 to 0 in this format. Let's see if our Borel set is like this, where for some arbitrary value of x being lying between minus 1 to 0, what's the probability of this pre-image of this Borel set B in this case? So we know that if we take the pre-image of the Borel set B in such case, it would contain the value of value corresponding to the random variable being minus 1. So when would the random variable be minus 1? We had seen that random variable was minus 1 when the event 1 occurred. So when the event 1 occurred, the random variable took the value of minus 1. Hence, if you take the pre-image of this Borel set B in this case, this would map to 1. So in this case, x inverse of B would be the set 1. And if you take the probability measure of this is probability measure of 1, we know that from our example we had defined it to be 0.2. Hence this value is 0.2. So if x lies between minus 1 to 0, the cumulative distribution function of it would take the value of 0.2. So let's write it here. Now let's see if x is present between 0 and 1, which is this case. Here, if my Borel set is this, it would contain two elements. So since 0 is also present and 0 maps to 2, we know that x inverse of 0 maps to 2. So the x inverse of this whole Borel set B in such an example would contain both 1 and 2. And we know that the probability measure of 1 and 2, since both of these sets are disjoint, we note that this would be the summation of individual probability measures. And this would be, let's calculate it, P of 1 is 0.2, P of 2 is 0.3. So this will be 0.2 plus 0.3, which is 0.5. Hence, the cumulative distribution function will take a value of 0.5 when small x is present between 0 and 1. Now coming to our last area in the real number line, we can say that let's take an example of small x where x is greater than or equal to 1. We know that it will contain all the three elements here, since 1 is also present in this range. So x inverse of 1 would map to 3. Hence, if you take a Borel set B, which is the set of real numbers from minus infinity to small x, where small x is greater than equal to 1, and if you take the pre-image of this Borel set B, it will contain all three elements. So in this case, x inverse of B would contain 1, 2 and 3. And we know that if I take the probability measure of this case, it would be same as that of P of omega, which is 1. Hence, for all the values of small x greater than 1, the cumulative distribution function will take up the value 1. So we have seen this is our example here. It's also being shown here, and if you want to have a visual representation of it, I have also drawn a graph of it. So you can say the value of the cumulative distribution function was 0 before -1. When it reaches -1, it shoots up to the value of 0.2, and it stays 0.2 until it reaches the value 0, and at x greater than equal to 0, it takes up the value 0.5 in this interval where x lies between the values 0 and 1, and if small x is greater than 1, then it will take the value of 1. Hence we have mapped the cumulative distribution function for this random variable. Now let's calculate the cumulative density function of the random variable x using this cumulative distribution function. So we know that the probability density function fx of x is the differential of the cumulative distribution function with respect to small x. So if we differentiate this, let's say we go from -infinity to 1, so we know the slope of this is 0 from -infinity to 1. So the value of the probability density function would be 0 from -infinity to 1. At the value of -1, it would peak to infinity. So I am representing this using the Dirac delta function. So this will be 0.2, this will be 0.3, and this will be 0.5, like this. So this spike here goes till infinity, but if you calculate the area under the graph, it would give out to be 0.2. It would give this value. Hence we have, similarly you can differentiate the cumulative distribution function of x and find out this probability density function. Here we have defined it